This video, we're going to discuss critical points of three-dimensional functions. If any of this is helpful to you, please leave a like. Let's get into it. So let's start by recalling what critical points are for two-dimensional functions. So we have some function. Say it looks like this, and we want to find critical points of this function. This is a critical point. This is a critical point. Why? Well, critical points are points at which the function, the inflection changes, where it's at its local maximum, where it's the biggest that it's going to be. If we went on and added a little bit more of the function over here, this would be a critical point. This would be a critical point. Now, these are local minimums, right? These are local maximums. What does that mean? It means, for the function that's next to it, it's the highest point. For function that's next to it, these are the lowest points. Okay, now let's sort of expand this idea into the 3D. So see that we have some function that takes place on this range of values here. And, in some spots, we've got hills, and in other spots we have divots, right? So say at these high points, we have, local maximums. That's a critical point. This low point, we have a local minimum. So that's also a critical point. But what you'll find is that in 3D, you actually have another kind of critical point, and that's called a saddle point. Now, if you were to look at a saddle point, it's kind of like the best way to think of it that I find is like a Pringles chip. So we've got our chip here, and we travel across it this way, and we make kind of an arc, right? And you got your maximum right there. But if you travel across it this way, you make an arc and you have a minimum right there. So it's a critical point, but it's neither a maximum or a minimum. It's kind of both. It's why it's called a saddle point. This kind of looks like a saddle, right? A saddle that you might put on a horse. All right, so we have our three kinds of critical points. Now let's figure out how you would find them. Let's figure out how you would find them for a given function. Before we get into a specific example, let's go through each of the steps that we're going to take when we do this for any of these functions. Keep in mind that the following steps are only, for the most part, are only specific to a function of two variables, not functions of 3 or 4 or 5 variables, although the general idea can be expanded to those higher numbers of variables, but it does get more complicated. So we're going to stick to two variables. Step 1 is going to be to find the partial derivative of f with respect to x and the partial derivative of f with respect to y. Step 2 is to set both the partial derivative with respect to x and the partial derivative with respect to y equal to 0 and solve for x and y. Step 3 is to pair your x and y values that you got out of step 2 together in all the possible arrangements to list all the possible critical points. The next step is to find the second order partial derivatives of f of x with respect to x and second partial derivatives xx, yy, and xy. Step 5 is to find the Hessian determinant. Now, this is where it branches off between multivariable with 3 or more variables and what we're doing for our purposes, which is just simply 2 variables, right? And for 2 variables, it's pretty simple. All that we're going to do is remember that d is equal to your second partial derivative with respect to x multiplied by your second partial derivative with respect to y minus your second partial derivative going with x and then y squared. So we have d is equal to, and this is what you need to remember, is simply that d is equal to partial derivative of f with respect to x, second partial derivative, and then the second partial derivative of f with respect to y minus the second partial derivative of f with respect to x, and then f with respect to y squared. For step 6, we're going to plug each critical point in. And what are we plugging it into? Well, we're going to plug it into our different uh, second order partial derivatives, and we're going to plug it into our equation for d. And all this information that we get out is going to classify what kind of a critical point it is, whether it's a local maximum, a local minimum, or a saddle point. So let's kind of draw out that decision tree that will help us decide what kind of point it is. So here we have our critical point. And first we plug it into our equation to figure out what d is, right? And we have 3 different possibilities here. D is greater than 0. D is equal to 0. And d is less than 0. All right. So let's start with the simplest one here. If d is equal to 0, the test fails. So test no work. Uh, uh, Smiley, frowny face. All right. So test failed to tell us whether it's a maximum, minimum, or a saddle point. In that case, you're gonna have to find a different method for figuring it out. Then we have the other 2 possibilities. If d is less than 0, then it's a saddle point. But if d is greater than 0, then we have to do further tests on that point to see what it comes out to be. So the first possibility, well, what we're going to be testing next is f of the second order derivative of f with respect to x, which we should have already found when we were looking for d in the first place. But if this number comes out to be greater than 0, then it's a local minimum. And if this number is less than 0, then we come out as a local maximum. And there you can see that we have all 3 of our different possibilities for the critical points. Now that we have this, then step 7 is to evaluate each of these points to see what the local minimum and the local maximum and the saddle point, what their values are. Okay, now that we have this complete list of all the steps, let's go to an example question and actually test this out. Okay, so in this problem, we're given a function f of x, y, and our task is to find the local minimum and local maximum of the function. All right, so let's look at this and go one step at a time. What's step 1? Step 1 was find the partial derivatives with respect to x and with respect to y of the original function. So let's do that. Step 1. Okay. Partial derivative with respect to x would be, let's see, 3x minus 6x, or 3x squared, my bad, minus 6x minus 9. Partial derivative with respect to y would be 3y squared minus 18 y. Okay, each of these can be simplified a little bit by pulling out a 3. X squared minus 2x minus 9. And then here we can pull out a 3, and we have y squared minus 6y. All right, that might help a little bit later. On to step 2. All right, set both of those partial derivatives equal to 0 and solve for x and y. Okay, we're going to start by setting the first one equal to 0 and solving for x. So we have 3x squared minus 2x minus 9 equals 0. Now we can just divide by 3, and that gives us x squared minus 2x minus 9 equals 0. Now in this case, we're going to factor to get our different possibilities for x. And in this case, we want something that adds up to give us, actually, see, I've already made a mistake here. This isn't a negative 9. When we divide it by 3, this becomes a 3. So that's a 3, my bad. All right, so we want something that adds up to be negative 2 and multiplies together to be negative 3, and that would be 1 and negative 3. So our two factors are x plus 1 and x minus 3. All right, so then our two possibilities for x, because either one of these could be 0 or both of them, is that x equals negative 1 would make this first term 0, and or x equals 3 would make this second term 0. All right, so we have both of our possibilities for x values. Now let's move to our second partial derivative and solve for our y values. So 3 times y squared minus 6y is equal to 0. Same situation where we can just pull out the 3 or divide by 3 on both sides, giving us that y squared minus 6y is equal to 0. We can factor out the y, giving us y and y minus 6 equals 0. And similar to before, y is equal to 0 will give us 0. And or y is equal to 6 will give us 0. All right. So let's move on to step 3 now that we have all of the different possibilities for the different variables. Step 3, pair your x and y values together to list all the possible critical points. Okay. So step 3. So what does that mean? It means each possible combination of x and y values we're going to put together. So the first possible combination is negative 1, 0. Second is negative 1, 6. Third one is 3, 0. And the fourth one is 3, 6. And that's all 4 combinations of x and y values. All right, on to step 4. Okay, step 4 was to find the double partial or the second partial derivatives with respect to x and y, and then x and then y. So we're going to find each of those. fxx, fyy, and fxy. Okay, so we're finding the partial derivative of, let's go find these ones that we found up here. I'm going to grab these and bring them down for reference so that we can look at them. Okay, so these are the functions that we're going to be taking yet another partial derivative of. So for f of x, sorry, for the second partial derivative with respect to x, we're just going to do that for this function here, which comes out to, let's see, 6x minus 6. And for y, if we did the partial derivative again, we get 6y minus 18. Okay. Or actually, before we get rid of that completely, we need to do the partial derivative of this function here with respect to y. But since there are no y terms in here whatsoever, it's just a constant, and then the derivative of a constant is 0. So let's put a 0 right there. All right, so we have all of our partial derivatives now. We can move on to step 5. So step 5 is to find the Hessian determinant, which is given by this equation down here. So let's do that. Step 5. D is equal to, what is D equal to? D is equal to fxx multiplied by fyy minus fxy squared. Okay, well, let's plug in our values for each of these. Before we do that, let's go ahead and simplify these down like we did the other equations. So we can pull the 6 out. 6 minus 1, or x minus 1, 6 times y minus 3. Awesome. Okay, so we have 6 times x minus 1 times 6 times y minus 3 minus 0 squared. And that simplifies out to 36 x minus 1 times y minus 3. Awesome. That's step 5 done. Step 6, plug each critical point in to sort of this decision tree that we have here. And then from this decision tree, we're going to find out whether it's a saddle point, a local maximum, or a local minimum. Okay, first though, we need to evaluate D for each point. So let's do that. So step 6, I'm going to do step 6 for each point individually. So that means we need to go find our list of points, have that for reference down here. And let's start with our first point. So for -1, 0, we have D equals 36 times -1 minus 1 multiplied by 0 minus 3. Now, we could solve this out and get some number, but let's remember what we're testing for when it comes to D. We want to know if D is greater than 0, equal to 0, or less than 0. And a lot of the time you can tell that without actually even doing any of the arithmetic, or very much of it anyway. You can tell just by looking at it that this is going to come out to a negative number right here. This is going to come out to a negative number right here. And so if we have 36 times -2 times -3, that's a positive times a negative times a negative. What does that come out to? That comes out to some positive number, right? So this is going to be greater than 0. Okay, let's go back to our chart. What does it say about greater than 0? Well, it says that we need to go do another test. We need to figure out if the second partial derivative with respect to x is greater than 0 or less than 0. And based on that, we'll know if it's a local minimum or a local maximum. So let's do that. Okay, so f x x is equal to, well, we already figured out what that was. It was 6 times x minus 1. And in this case, our x value is -1. So this is 6 times -1 minus 1. And again, we only need to know whether it's greater or less than 0. And in this case, we can clearly see that it's going to come out to be negative, so it's less than 0. And therefore, this point is a local max. Awesome. Okay, so that's 1 point down and 3 more to go. So next point that we're going to do is -1, 6. And our d value is going to be 36 times our x value, which is -1 minus 1. And our y value is 6 minus 3. And you can tell by looking at this that it's going to come out to be a negative. We have a positive number. This is going to come out to be a negative number, and this is going to be a positive number. And so all that's going to be less than 0, which means if d is less than 0, then it's a saddle point, right? Okay. So we don't have to do anything more. We can say that this is a saddle point. All right. Next point is 3, 0. Okay. Let's do our b value to start with. D equals 36 times our x value, which is 3 minus 1, multiplied by our y value, which is 0 minus 3. And then we can tell by looking at this is kind of a positive number. This is going to be a negative number. So this is also going to be less than 0, which means that this is also just a saddle point. All right, now let's look at the last point, which is 3, 6. Now you might guess, just because, we haven't found our local minimum yet, that this is probably going to be the local minimum, but let's go ahead and run through it anyway. So our d value is equal to 36 times 3 minus 1 times 6 minus 3. Okay. And this is going to be a positive value on both of these, right? So positive times a positive times a positive is a positive, which comes out to 0, or being greater than 0, sorry. Which means that now we need to go to our next step of evaluating what the second partial derivative is with respect to x, which, like we said above, was 6 times x minus 1. And our x value here is 3, so 3 minus 1. And that is equal to something that's greater than 0, right? And that means that this is going to be our local minimum. Local min. All right. Now, what was our last step? The last step was to evaluate our function at each critical point, just to see what the value comes out to. Now, what the question asked for, though, if we go back to the very top, was to find the local minimum, right? Find the local minimum and the local maximum of f of xy. Now, what that's asking for is what the value is at the local minimum and the local maximum, and it's asking for, what is the coordinate of the local minimum and local maximum. Well, we already found the coordinates. We just need to find what the minimum and maximum values are now. So we're not even going to bother evaluating the saddle points. You could if you wanted to. We have everything that we need to do so, but we're not going to bother with that. Instead, we're going to go up, we're going to grab this function here, we're going to do step 7. Just going to do each of the minimum and maximum points. So let's start with the minimum point. So, which would be f of 3, 6 is equal to, and then you just plug everything into the equation and solve. For your local minimum, you get negative 135. Okay, so 135 at 3, 6. That's part of your answer right there. And now let's find the maximum. So max would be evaluating the point at, let's see, what was our maximum? Negative 1, 0. And we'll just plug in and solve for that. And after you solve that, it comes out to 5. All right, so then you have a maximum at 5 of 5 at point negative 1, 0. And that is the second part of your answer. Okay, just to review everything that we did here. We started by taking our equation, finding the partial derivatives with respect to x and y. Then we solved each of those partial derivatives for x and y by setting them equal to 0. Then we found each possible point by combining those x and y values. Then we, for step 4, we found the second partial derivatives. For step 5, we calculated the Hessian determinant by using this equation. That should be fairly easy to remember. In step 6, we used the Hessian determinant that we came up with, equation, and the equation for the second derivative with respect to with respect to x, to figure out whether each point was a local maximum, local minimum, or saddle point. And then in step 7, after we figured out those points, we plugged each of those points into the original equation, right? And we evaluated what those values would be. So we figured out what our minimum is and what our maximum is. All right, thank you for watching. I hope this was helpful. If it was, please leave a like and consider subscribing. Have a good day.